Log on, tune in, find out. Another good idea from Cambridge.
Speaker is Jeff Wu from Georgia Tech, who has agreed to open the conference, and he's going to give a talk about post-Fisherian experimentation from physical to virtual.
First, I'd like to thank the committee for inviting me to this conference. I apologize I cannot stay longer because next week, SAMC in the US has another program, a workshop on a very closely related theme. And unfortunately, I am on its leadership committee. I cannot get out of it. Actually, I tried to ask them to reschedule and it's impossible. And the end result is I predicted to them that a lot of American speakers from the American side will be stolen by this conference because of the name of Newton and the name of Cambridge. So, and it happened. So you see a lot of my fellow Americans here. So this is a slight adaptation of my Post-Fisherian lecture I gave in Miami during the JSM. And I know that when I choose this topic to give here at Cambridge, I have some trepidation because speaking about design experiment here, especially in Cambridge, is a bit like bring the coal to Newcastle. And if I use a Chinese phrase, there's another one interesting is you give a lecture in front of Confucius' house. Okay, so here I go. I will start with Fisher's legacy. And this one is for experts, so I'm skipping most of the historical background except for a few interesting notes or stories. And I will move to really focus on the post-Fisherian work in factorial experiments. And remember this very long period from about 1916, I have the date on the next slide, 80 some years. So I'm just taking a few snapshots. So I would describe three principles for factorial effects. These are sort of addendum to Fisher's fundamental principles. And then the next one is I'll outline some new research I've done, which sounds very simple, but surprisingly, I think it's new, which I call conditional main effect analysis. Then I'll move to the second part, to the virtual world, or what we call computer experiments. Again, this field is expanding really fast, and with a lot of results. I would focus on the two modeling approaches, the stochastic modeling and the numerical, the two approaches and their relationship. Then some the concluding remarks. So in October of 1919, and I was so glad to hear that we're going to trip to Rothamsted, so that goes well with my talk. Fisher, after a period of unemployment actually, so don't be surprised Fisher didn't get a job. But remember there was about a time after the war, First World War, I think, or you call it Great War in the United Kingdom. Okay. Fisher got a job at Rothamsted. And so according to the memoir by John Russell, Sir John Russell, who was the station director, Fisher's job was to examine our data and elicit further information that we had missed. And so there's Fisher. Then the rest is history. In about 7 years, Fisher made two breakthroughs, the ANOVA and design experiment. Most of us would take 7 years to figure out a few good ideas, or maybe struggling, and or even very good people would take more than that. But Fisher being Fisher. Okay. So these are three fundamental principles of Fisher. I don't need to say much. Replication, blocking, and randomization. But I'll come back to that later. for a good reason. Okay, so factorial experiments. Well, again, I think the first major paper was by Fisher, 1926. Then, of course, I think it was Yates who did a lot of work. And I believe Yates never had a PhD. I think Yates had no doctoral degree, I think. And Yates' initial work was not statistics. Interesting, I read a bit about Yates. So Yates did a lot of work in factorial design. And later on was David Finney, who worked on fractional factorial, and I come to that later. Both were working with Fisher. Well, I did this slide because it was a Fisher lecture in Miami, so I had to somewhat relate mine to Fisher. Here, probably it's, you know that already. And Finney was one of very few doctoral students of Fisher. Fisher took very few students. Probably difficult to be Fisher student or work with Fisher. And the CRR was another one. Okay. Now, factorial experiment had a big revival, sort of another period of heavy development. And especially, I would say the Wisconsin School by George Box and others. And I was very lucky that I started my career after Berkeley. My first job was Wisconsin. So I witnessed a lot of major work at that time. And the main reason is after the war, factorial experiment, the application of factorial experiment, a lot large scale, much larger, more complicated experiment. So highly fractionated, more complex structure. It's very important to understand, usually major theoretical advances is driven by application. You should understand the historical background, the application that drives the theory if you want to do good research. Okay. Well, so when Mike Hamada and I start writing our book on design experiment, we call experiments, we were sort of, one of the first questions was, what are the governing principles for factorial experiment? Remember, Fisher had 3 principles for general experiment, but nothing specific for factorial structure. Okay, so here are 3. First, we call effect hierarchy principle. So maybe I should stand on this, I can read mine. The lower order effects are more important than higher order effects, or likely to be more important if you, and you can put a Bayesian statement later. Effect of same order equally important. Next one called effect sparsity principle. The number of relatively important effects is small. By the way, these principles are not as fundamental as Fisher in the following sense, that you need to put some qualification statement. Like the second one, the effect sparsity, really for screening experiments. When you move to the highly curved side of the surface, this doesn't apply. Okay, but I don't have time to go into a lot of elaboration of the principles, but we can talk later. Effect hierarchy principle. For an interaction to be significant, at least one of its parent factors should be significant. So they were first spelled out in our book. Okay, so I'm going to give some interesting historical note. Actually, I was aware some of these ideas, maybe in the exact writing by the old masters, but for the Fisher lecture in Miami, I had to dig into the writing, and I found some, and to my satisfaction. The term was coined by us, but I knew this was known very early on, even ever since I taught design experiment in Wisconsin. So you read different books, and there will be a sentence, a phrase here and there, sort of implicit. Well, and you go to Yates, the 2 major papers, well, 37 is really the expansion of 35. Okay, 35 is a very fundamental paper by Yates. There are 2 quotes. To save time, I only read this quote. High order interactions are usually of less interest than the main effects and interaction between 2 factors only. Okay, and I have the page number. Well, the more precise version that we have and refined by our student is very useful in choosing or in justifying sort of, so for those who do optimal design, factorial optimal design, in choosing optimal fractional designs. For example, how to justify maximum resolution criterion or minimum aberration criterion? You use the effect hierarchy principle. Because why do you guard against, worry more about a lower order thing being sacrificed That's the hierarchy principle. But that's really implicit. I don't want to get credit for that. I don't have time, so I do not say much about effect sparsity. Okay, there's another story, but I would not. Effect hierarchy was coined by Hamada and me, and this was originally used to rule out our purpose was different from others, was in model selection. And this one I wasn't sure, but I was really happy. And when I read the part, and again Yates. Okay, so this actually not in the 35 Yates, in the expanded one. This like a little book, 95 pages, 90 some pages. And nowadays, especially in the U.S., students don't know this. Students know machine learning, bioinformatics, survival analysis. I don't think they would know this one, the Imperial Bureau of Soil Science. This is what Yates said. And on page 12, factors which produce small main effects usually show no significant interactions. Okay, they have quite a few quotes, but this is the one that's most relevant. Okay, then Hugh Chipman in his Waterloo thesis, he was a student of Mike Hamada and me, current editor of Technometrics. So he did both the strong and the weak version of hierarchy, and using the Bayesian one. Naturally, Bayesian is a very good approach because you can quantify the strengths of hierarchy, sparsity, or heredity. Okay? And of course, I have to say that the strong hierarchy is the same as marginality principle by McCullough and Nelder, but with a different motivation. I think a long time ago I spoke on that, and Professor Nelder, who passed away, and I admire him a lot. He said about the principle. Of course, I told him I was aware of that. It's in the book, in the famous book. Our motivation was, okay, I have a story about it, but probably I don't have time to. A story about how we found it. Basically, I'll give you one little tip of the story. There was a quality delegation from Wisconsin and Bell Lab to visit Japan, and this was afternoon in Nagoya, very hot summer. I heard some presentation by the Japanese on quality studies, and there were very successful case study based on experiment, what Taguchi called L18 or L36. Those are complex aliasing, and this is my terminology, but they never analyze interactions. So anyway, there was the reason, but I'll get to that. So then I was thinking that there's something there. Okay, so let's use this data set to illustrate the idea, how we got this idea. So this is a 12-run Plackey-Berman design, but only used for this real data for 7 factors. These real data came from a metallurgical engineering journal. And what is well known about Plackey-Berman design is that if you estimate main effect, you also estimate a lot of aliases, but with coefficient plus minus 1/3. Those are the interaction not involving the main effect. So when we start writing a book, I call these partial alias. Of course, this is different from partial confounding, and the meaning is very different. But I thought there is a confounding, partial confounding by Yates, but this has a different meaning. That when you have two vector, two sort of contrast that's parallel, it's alias. When it's in between, not orthogonal, then it's partial alias. Well, but this is a key part. That here you count, if you have used up all the columns, you have 11 factors, not counting the current one, you have 10, choosing 2, you have 45, the interaction as partial aliases. And this is, I call it complex aliasing because, and the reason is I was aware of that for a long time, but the traditional is viewed as a disadvantage. If you go to Casper Daniel book, nowadays his book is not popular anymore, but the book was, in my time was used in textbook. And Daniel called these one hazards. Okay, and actually Hamada, he was actually first doing part of this thesis, And he went to talk to like Norman Draper, and Norman Draper, oh no, this is no good. This is, this is the one. So anyway, so in Wisconsin, we somehow missed one step, and I'll tell you the step. Okay, so because of that, the standard textbook paid little attention to this design. But this design was first widely used by Taguchi. But I don't think he understands the fundamental reason. It's just because the economy of the run size, that you can do a lot of, you can accommodate a large number of factors. Okay, so make sure okay, so this is the strategy Hamada and I have in the JQT paper, 1991. First, use effect sparsity to realize that although that if everything is significant, it's a complex relationship, but many of them are not significant. You don't know which one. The number, if you do a model selection, the actual number is small. So complexity disappears. Point one. That we knew. But point two, we found in Waterloo. There was one day I said, gee, that problem, I'm sure there should be a solution, because I knew the Japanese, so many studies, they were successful, they were complex. They didn't bother to analyze the interaction. There must be something there. And then we revisit our analysis, and suddenly, I remember it was on hallway, and we said, in our model selection, there were too many incompatible models, so we used hierarchy to rule our model. He suddenly remind me that their model without A, B, without a mother or father, without A or B. So we did that. And next morning, I saw him, he was smiling with a big smile. I knew, and he showed, look at the result, and I'm going to show you the result. Okay, so there's a frequentist version, and there's a Bayesian version by Hugh Chipman. Well, I have to say that this is effective only if the number of interactions is small. Okay, so if you go to the original cat fatigue experiment, this was in the original analysis by the author called Hunter, but it's a whole D Hunter, different Hunter. Okay, and actually they made a remark that is that they couldn't interpret the result. That is, if you try to do optimize engineering, usually after running experiment they optimize, and the conclusion was contradictory to the interpretation, the intuition. So what we did was, if you do this analysis, actually D doesn't appear, but it's an interaction Fg, and R squared double from 45 to 90. And also the interpretation is consistent. And this detail can be found in the book. Another data set, also real data, this is 3-level. This 18-run 3-level experiment. And the original author, well, usually if you have such a complex experiment, you just run as main effect. Anyway, so found E and F. But now what's more interesting here is do this analysis, you found totally different factors, B and BH and their interaction. And the reason is that E and F and BH has some partial alias. If you calculate, you find out why. So only when you do model selection, the right term, the correct term would be selected. Okay, so I'll skip the other. Now I'm going to move to something else related, and this one is how to de-alias alias effects. These sound contradictory, by the way, for resolution 3 or 4. Okay, anyway, let me give you a review. The two-factor interaction, two of them called A, B, and C, D, and well, first terminology by David Finney was called alias because these two represent the same contrast or same column. Okay, so Finney used the term alias because in distinction to confounding, and I know at least in the US, quite often even in writing by young designer, alias and confounding got mixed up. I remember John Nelder was actually in a meeting, someone used the term alias and said, this is confounding, that you Americans don't know how to use English, and he was right. So confounding, so I repeat for young people, but on the British side, I don't think you have a problem. But as a Chinese, I'm going to teach you some English. So confounding is between a block and a treatment. and aliasing between two treatments. Okay. But remember, all this legacy came from this side of the world. Okay, so now, for example, you have resolution for design. These two columns, A, B, and C, D, are identical. Okay. Well, so I purposely call these fully aliased in the book because it's in contrast to partial alias. Well, so usually we would say these pair effects cannot be disentangled, so they are not estimable. So the question is, actually, this is a bit provocative. Can they be de-aliased without adding runs? I put 2 question marks because you say, how can you do that? Okay. There may be one way of doing. So here's a hint. Well, you should not look at interaction as 1 degree of freedom. You should view interaction as part of 3-dimensional space with A, B, and AB. Then next step is now you have this space and CD you have another space, but AB and CD are identical. The joint space is 5 dimension. In order to do that, now reparameterize. If you don't reparameterize, you cannot do it. So how do we reparameterize? And this was, and actually in our book when we define interaction, this is how we define interaction. First, we define conditional main effect. So given the plus level of B, the conditional main effect of A is the difference between A plus and A minus at B plus. And you can define the other one similarly. And then the difference of the two is the interaction. Of course, you go back to Finney's first paper, the algebra was there. Okay, but I read very carefully. I don't think there was a lot more explanation. But remember, this is no big deal. Why? How do you define second derivative? It's a derivative of first derivative. Or more proper analogy, how do we define a second order, a finite difference? Is the difference of 2 neighboring successive first order differences. That's the one. Okay. Okay. So so what I suggest, we can view conditional main effect as the 2 interaction component. That's another way, not the only way, but another way of looking. So now let's do the aliasing. Okay, so reparameterize the 3D space as this, another one as this. In the joint 5D space, remember some of them are not orthogonal anymore. Not orthogonal. Because in the previous one, the 6D space, 2 of them are identical, the other 5 are orthogonal, but they would not do it. Now you can see the idea came from my previous work. Well, actually, I knew this earlier. That is, this non-orthogonality that ever since about late 80s, I realized was something you can exploit. And I used it in the previous analysis in the complex aliasing. Okay, so now once you realize that some of the conditional main effect can be estimated by variable selection, so I call this one CME analysis. Of course, conditional main effect are being used in different places. Even Mike remind me our work on the sliding level experiments. Whenever you do like nested modeling, nested effect is conditional. And Terry Speed recently had a paper, and Rahul Mukherjee wrote something. So CME being used, but our purpose here to de-alias, so it's different. Okay, so non-orthogonality here is a saving grace. I don't have time here, but I believe, I mean, here I don't need to say that, but you know, public lecture, most people are not design experiment, industrial. They're probably working on pharmaceutical, and they use a number of factors very small, or social experiment. But what I would like to say is in social and medical studies, with fewer number of factors, you can use that. And actually, I gave this one at a workshop at Harvard, and Don Rubin was quite interested in that for some social study that he had been conducting with Tirthankar Dasgupta. I hope he was able to fly here from Boston, so didn't see him. Okay, so now use real data, and this is the Canadian data when I was the GM chair, and I'll give you another story. So, not yet. So here, this is just the representation. the red one, remember you had the space on AB, and the green, the space on, so you A, and these two, C, and these two, 6, and the maximum is 5. Okay, now here the data set that I got in Canada, 88. Actually, I have this idea in 88. I never published it, and it was in my drawer. And once I jokingly told my wife, a few years ago I was sick, and told my wife, gee, if I die, this idea will die with me. It's bad. This is one of the good ideas. I really worry about that. And but because it was very easy, simple, so for Fisher lecture, I dug out, and I found out, yes, 88. Okay, I have my notes on the back of computer printout. I won't have time go into detail about this, but it's a 16-run resolution for design, and all the two-factor interaction are aliased. Okay, and this was a production simulation experiment. Okay, data. And if you do standard one, remember, standard one resolution for, you give up on resolution, on interaction, you cannot do it, period. So you try to do, but remember the CF is alias with DE. CF with DE, okay. But now, next one, if we do the CME analysis, you don't choose the C or the CF. You can see these two. You choose C given A plus, and then you can choose the A. So and then you look at the CP, this is improvement. But there's also a meaning of that. That if you go to the interaction plot, you look at this is the one that's significant and has an engineering meaning. It means, well, C is the lane selection logic that when you do production, when vehicles or units come into a station, how to arrange them. It's like traffic control, okay? So this is significant on the simulation output only for a larger cycle time at the marriage station, not the shorter cycle time. So you can see here, the traditional 1 degree of freedom interaction will have much less engineering meaning than this one. Okay. I want to be on time, so actually I think I'm pretty okay. So I'm going to move to the physical world, the virtual world, and I guess doesn't take a lot of convincing because one more workshop will be on computer. I really wish I could be here, but I had to go back to SAMSI because they shoot me. I agreed to be on the committee. And we had a meeting quite a few months before, and I told them try to, but they have scheduling. They cannot change anything. Engineering side, but I do want to say that the computer experiment was used by especially aerospace people very long time ago. Why? Obvious. How many aircraft do you have? You have only one space shuttle. You have a few aircraft. And you send to the sky, one may get crashed. So you run all the simulation. Actually, at Georgia Tech, because it's a big engineering school, I mean, in addition to others, I work with mechanical and the aerospace. They run a lot of simulation. And they run Kriging. And the reason pretty obvious. But it's more than that. For example, I'm now engaging in a material simulation. It's not here. Nanomaterial simulation. It's a different kind of simulation, not a finite element, but first principle, and take a lot of time. You need to monitor all the atoms. Another one interesting is in biology. In drug design, for example, we have drug, pharmaceutical companies in polymers. So this is cover everything, and the traffic, and it doesn't have to be just engineering and science. This is one example that I was involved. This ASME, Mechanical Engineer Journal. And in this case, there were actually a lot of design parameters. This design heat exchanger, a lot are the dimensional or first the shape, the topology, or you can see dimension, many different dimensions. In actual industrial design, this can be 20 to 80 input parameters. But in the ASME, we choose a few. Okay, and your temperature, there's another type of design parameters, or some environmental conductivity of solid material property. Okay, and this is flow rate of air. Well, in some ways representing like fan, if you're a fan too. Okay. And output from a finite element is the total heat transfer. You want to get the heat out as soon as possible. Okay. Very big application is the data server, the big data server. Okay. So this is actually a big deal. And then use finite element analysis. Okay. So here, so in this case, you can use Fluent to do that, which is very well known, computational fluid dynamics. But it can take a lot of time. And this is not the most notorious. As I said, like material simulation, nano material simulation. I think the same in drug design. Very time consuming. I'm really time consuming. And of course, meteorology. Okay. So anyway, this was in a paper involving Roshan and ASME Journal of Mechanical Design. So why computer experiment? I don't need to preach to you. It's obvious for reason of cost or time, but another one is feasibility. You know, like if there's a forest fire, you cannot generate another fire. You observe a fire. You have some flooding, you observe flooding. Plus the simulation parameters and those you observe, they are not identical input space in those. So that's another area I haven't seen really very major breakthrough. So this area has many, many interesting problems. Okay. So now, actually, question back to Fisher. You don't use Fisher's principle here because, well, actually, for deterministic simulation, but even for stochastic, stochastic you may replicate, but depends. I mean, that's another long story. But you don't block, obviously. You don't randomize. What do you randomize? Okay, so not those principles. And I also doubt the factorial principle I outlined would be very useful, except for modeling the deterministic part. When you do this kind of computer experiment, you have the modeling two part. I mean, if you do kriging, you have the stochastic process, Gaussian process, but you have the mean part. But that we know what to do. So I think this is for someone ambitious young person. This is a good thing. It's not going to give you a lot of paper, generate a lot of paper, win a few small awards. But this is a fundamental principle for you to think. So maybe in a few years we're going to find out some nice principles. But I think my guess the principle will be related to applied mathematics, and I have some slides later. Two approaches to modeling: stochastic and primary kriging and numerical. I'm going to do more numerical. People here probably know kriging more. So this is a kriging model. I briefly introduced, not everyone knows. You have a Gaussian process and with a positive correlation function. Okay, but this correlation function is a function of the input. So you have x1, x2, and you put sort of some distance between them, and theta I would be something called a correlation parameter. It governs the smoothness or ruggedness of the surface. You can say that way. So when these 2 points get closer, correlation become 1. That means what? The sample path, the under sample path would converge. So it's continuous. Okay. So it sounds, well, that's just stochastic process. But what's interesting is this slide. Is when you do predictor, you use the blob, the best linear unbiased predictor, or called kriging. Okay. So this is a predictor. Well, this part is the regression part. Okay. So generalized least square. In this part, this is a residual. Now multiply by the inverse of R. R is a correlation matrix. So you can see every entry is a correlation between any 2 points. Okay. And the story about this interesting. And little r vector is the correlation vector. And this has this one key property, interpolating property. Now, let me comment on that more later. Well, let me say here. When you have deterministic simulation, you get fixed input, fixed output, the same input, same output. Now, if you have this data to build a model. You really want your predictor to be an interpolator. That is, whatever being observed, you should go through that. Okay? And not so much so for stochastic simulation. Okay? Of course, we can mildly violate that. That's just another research. There are a lot of research in this direction. Is that I don't have time. So the unknown curve, the true function is the black one, and if I have 5 points, kriging would give me this one. The kriging is stochastic, so you can get prediction, like confidence interval and so forth. And now if I add one more point, it's very adaptive. Then you put a different curve. Now you update the curve, the brown curve, go through this point, so that 95% interval shrink to 0, and all the other interval also shrunken. Okay. I like to use this slide to explain the idea. You have, say, finite element or some other computer modeling. Then based on that, this is our job, statistician job. Okay, if we do that, then we have little job, not a lot. So, and the reason we do kriging is we have statistical model which is very easy to compute. Instead of 3 hours, maybe 10 minutes, or actually less. Usually, the only problem is stability of the R inverse. Otherwise, we're fine. Okay, but the nice thing about this one is the two-way street. That you get a kriging model, you can use it to do prediction. And this was used so much in mechanical and aerospace design. It's long before we enter. You go to ASME journal and other mechanical journal, there's such papers in the 90s, aerospace in the 90s. And the two community didn't talk. I still don't talk a lot. But same thing at least bring in the engineers and the statisticians. Okay. So for example, well, you could do some prediction, and then your collaborators say, well, but this doesn't look right. Fine. Go back and do more finite element and build again. So the nice thing about you have that. And then you can do prediction, this, or do prediction. You can bring in physical observation. So that's my, of course, I need to give some historical comments otherwise. Kriging was actually coined by Materon, and but he gave credit to South African engineer Krieger. Krieger did this empirically. Okay, he was the first one. But the blob was derived by Materon. But blob is so obvious, of course, he couldn't be the first one. There are a lot of people. So why don't I mention the most famous one, the Wiener and Kolmogorov, they all done that. Jaglom brothers, and many people. Kriging was widely used in spatial statistics. But in computer experiment, as far as I know, but I heard it from my colleague Will Welch, Jerry Sachs and others, they publicated in the early 80s. Okay, so they were the early ones. Now, what are the main differences? Because if you do research, and some people say, oh, this is not new, it's kriging spatial study, and a student gets scared, oh my God, I'm working on something, I'm in trouble. You're not in trouble. There are there are some differences. One, for example, in spatial study, you may not care, you don't care about interpolation. Here you care more. You either like interpolation or you don't want a very severe violation of interpolation. Next, we have design experiment issue. Because we have input variable. We usually a large number of input variables. In spatial state, they are, but usually the number of input variables is smaller, usually observational. Okay, there are some, but not the same. And as a result of these 2 and 3 is the variable selection issue and response optimization are more acute. Okay. Problem with kriging is one key problem. If this R matrix is prone to yield conditioning, so numerical problem, especially when n is either n large or the dimension p large. And I have a paper with a co-author, even with some theoretical result using algebra to show that. Okay. And so this is one slide I didn't do in Miami, among others. Where is the interplay between design and modeling? So people will say, oh yeah, we have Latin hypercube for computer experiment solved. Well, not quite. I think a lot of people here are theoretical designer, I know, and these are my friends I've known for many years. This is an area I believe you can do a lot of new research. Here are two examples. One is if the statistical problem is you run simulation with different level of accuracy. The first really major paper is Kennedy O'Hagan. I think Tony O'Hagan is in North Carolina, SAMC, because I'll see him next week. And Peter Chen and me, and this was Peter Chen's thesis, all did some work. Well, that's on the modeling estimation side. And then, but question is, if I need to design experiments, say finite element or two different resolution level, then what do I do? You can say, oh, I run one Latin hypercube, another Latin hypercube. But what's their relationship? Okay, and this is what Peter did. It's mostly his work. You know, I'm a token co-author of Peter. Okay, he was invited, but I think he's waiting at home, expecting the baby to come in the next few days, so he couldn't come. Okay, and so this called nested. That different thing. Nested space feeding design. Various papers that he did with his students. This is after thesis, after he moved to Wisconsin. Another one is Gaussian process model with qualitative and quantitative factor. There are two papers. Our paper, this Wu is another Wu, not my son or someone, is Huaiqing Wu, okay, Iowa State. And Tom and his student Han, they had a paper both in technometrics. Okay, so this one, okay, I have time to give a story. Because actually I have a lot of story I skipped. This is an interesting story. I sent Peter to IBM as an intern. He was there for the second summer. He was about to finish. He came back, he told me, but Jeff, I was running this Fluent, the computational fluid dynamic simulation. But there are a few, I don't have slide here, but because, and there were a few qualitative factors. How do you do kriging? And what people do is just ignore the treat the qualitative as quantitative and run Gaussian process. Okay, so what he did was he built this stochastic model. Basically, play game on a covariance matrix. Okay, because every discrete level corresponds to a Gaussian continuous process. Your different stochastic process, how to put it together, and these are done very beautifully. But now next one, and this really is work, is the design. So quite a few papers. Construction of slice. An ideal slice is this. Slice meaning one discrete level, one slice. And I remember I said to him, I had a paper, this is one of my least cited paper in JSPI, and it's called Central Composite Design with Qualitative and Quantitative Factors in JSPI, I remember. And there were other papers like Draper and John in Technometrics, I remember. But this one, it was a more general construction, but the main idea was slicing. You slice, every slice corresponds to a more coarse model, because smaller data. When you combine all the slices into a more comprehensive model. But that was for a parametric central composite design, and that's different, and so he did that. But later, interesting, this slice space fitting design idea has been used by him outside design in cross validation, using to choose different cross validation samples. So you should go to the website. There's just many creative ideas that he had done. Numerical approach. Well, computation can be faster and more stable. Can also fit non-stationary surface. Okay. Now the problem is only a few of these numerical approaches have inferential capability. For example, you do the radial basis interpolating function. This one, in some key cases, can be shown to be equivalent to kriging. It's an interpolation, and actually, you look at math, it's pretty obvious there's something. So you can just piggyback on kriging and do inference. A more famous one, earlier one, Grace Waba worked on smoothing spline. And that one, you have the underlying reproducing kernel Hilbert space, and so. But in most cases, you don't. We can name Jerry Freeman Mars neural network, and Roshan has a method called regression-based inverse distance weighting interpolator. He was able to cook up a variance estimate based on the algebra but the method has no stochastic structure or element, so he still cannot. This paper, I think, appeared in technometry and no inferential capability. The one I'm going to do is when the approach is based on sparse representation, then we can do that. So anyway, so this what is now called UQ, uncertainty quantification. That's the main theme of SAMC in the US for the whole year. Okay, I'm going to explain this one. This is the idea. So now, using the same slide, often this is the UQ. So what's UQ? You think about it, if I do a numerical weather forecast, but the consumer who watch the TV and will say, well, but I want to know the confidence of your statement, because do I need to bring an umbrella or small umbrella or big umbrella? And depends on 95%, if I'm very statistical oriented. Okay, so this way the UQ really came from applied mathematicians. Okay, so you see, you can do UQ here. That's easy. The reason you have stochastic element. This one you need to do more clever work. And this way, I think there'll be a lot of new research. I'm going to give one example, but to save time, I'll skip the engineering meaning of that. Otherwise, I would not be. This on bistable laser diodes, and but anyway, this underlying surface is very spiky and jagged. And actually, each simulation will take a lot of time to compute. This one is a Lyapunov exponent in dynamic system, and actually, this related to a optical communication. Okay, I'll come to the next slide. And the purpose in this design is to identify as many positive Lyapunov exponents, those red peaks. So this is a surface that my co-author generated by using a lot of computer time, doing mostly parallel computing to get these results as the underlying surface for simulation. Other paper didn't get published, so we do that. Okay, so I would not do much about scientific meaning, but basically, the more positive Lyapunov exponent you can find, the more secure communication channel you can identify, and there's a better security. Okay, so that's the engineering meaning. So we want to search for as many PLE as possible, and also we want to predict, obtain predictive values, and also as a confidence interval. There's another issue I do not have time, is the sequential design of that. And the sequential design need confidence interval in order to go to the next step. But this is all numerical, so you need to build a stochastic element to do that. Okay, so we need build some stochastic element, or a fancy term, a UQ, to do that. Okay, so this approach, let me first explain. This is what we call over-complete basis surrogate model. This is our paper that appeared. First, using an over-complete dictionary of basis function. So this can be a dictionary. I mean, this is a terminology used a lot in machine learning. 1,000 or more. But every function is a known functions, like sine x, 2x, 3x, 4x, and so forth. No unknown parameter. This is a key thing. So now use a linear combination of basis function. So only thing unknown is the linear coefficient. This is a key thing. That is, you pay something, you have very large space, but you deal with linear parameters. This is really the key idea in sparse representation. Then using matching pursuit algorithm. I mean, there are different versions, again, to identify non-zero coefficient. And so usually use a very fast and greedy algorithm, okay, to do that. So if you have a dictionary about 2,000, for example, like in this case, use about 18, 19 of them are, and you put them together, there is an approximating function. It's incredibly accurate. But one more trick is you need to choose a basis function to mimic the shape of the surface. Sometimes you can do that, sometimes you cannot. Like in this case, we know that this is very spiky. So they use something called Gabor function, commonly used in image analysis. Okay, so this is a paper with two co-authors from Taiwan. They're all American trained. and in IIE, in Industrial Engineering, Transaction on Quality and Reliability. So how do we do stochastic structure? This is the one I refer to. M is very large, function known, Cj unknown. So what we do is we put a Bayesian prior on the coefficient Cj. Okay, on Cj. So this is very large. However, an actual number of coefficient being significant is much smaller than M. Remember, this is our friend effect sparsity. Right. So I use each principle once in my talk. So now what we need is a collapsing scheme in variable selection. And clearly, probably the most commonly used is this called SSVS, very well known. Stochastic Search Variable Selection by George and McCulloch. And one reason is that you can choose prior to represent your knowledge of effect sparsity, or you can tune. You can change the prior, so you end up having more term or less term, and so forth. So, and then the rest you do MC. You get a lot of the output connects curves. Okay, so for example, you look at, it didn't come out with the color. There are two colors, green and black. Okay, left to right would be the grid point of the surface. From left to right, you remember all the spiky things on the right? On the right, you see, so you have peak, valley, and this is what you see. Okay, but next one, color didn't come out well. Anyway, the middle one is a median from the MCM simulation, and you have a point-wise 95% Bayesian credible interval, lower and upper. So basically, I show you one example here. You can do uncertainty quantification very well and very simple. Okay. So now I'm done. So Fisher's influence, and Fisher actually graduated from Cambridge, so continue from agricultural to industrial experiment, actually to everything. I'm talking about only design, every facet of design, the Fisher's influence. And they were, especially for industrial, the new concept after Fisher, like the three principles, the methodology like box response surface. And for this talk, I do not have time. I didn't do the perimeter design that was first pioneered by Taguchi, but most of the methodology were developed in the West, and particularly in the US. And that I was part of that in from 80s. So these further features legacy. Well, as I said, I think we need some new guiding principle for computer experiments. And several common. Kriging can a numerical problem. You can do different tweaking or kriging. You can put a nugget, or you can do tapering. And there are other, but these are probably two most commonly used. And I think that one has still need to see some research. Also again, faced with applied mathematics. The numerical approach, and this I think I see tremendous opportunity, need uncertainty quantification. And this way, statistics and applied mathematics would, we rarely see stat and applied math really work together. When we run MCM, we carry on our own. I think statisticians were the key players. And I think design experiment would also have tremendous opportunity here. And you have to explore the interplay with modeling. What model, what design, not just a Lightning hypercube. Lightning hypercube you are beating a dead horse, I think. Thank you.
Thanks very much, Jeff. We have plenty of time for questions or comments.
Me?
Yep.
Okay. My question is about. You said that randomization is not of much use in computer experiment. I'm not much sure about that.
So how do you randomize?
Eh?
So how do you randomize?
Well, for example, I know at least 2 papers. In one, there is an FEM model, and the geometry of the finite elements is randomized in a mechanical experiment, in a simulation of a mechanical experiment. And another where you can take kriging and not just take, for example, a Latin hypercube, but sample a random Latin hypercube and try to deduce something from the fact that the Latin hypercube you are using is actually randomized from the set of all good Latin hypercube possible in that experiment.
I think
in principle, I want to say in principle, it's, I don't see any precise reason why randomization should not be used in a computer experiment.
I think your 2 examples, the randomization, the term but used different for different reasons. Take the geometry. I can choose a few geometries deterministically, or I can choose it randomly. That's different from Fisher's original randomization, I believe. But certainly you're right. Especially the second one is more convincing that they do randomization in like queuing model, the stochastic simulations. For example, the perturbed input for sensitivity analysis. That I wouldn't call randomization. But you're right. Your examples are good. Maybe we had different. Maybe I should make the statement with some qualification. Yeah, but I think they mean a bit differently. Yeah.
Julian?
Your principles, hierarchy, sparsity, heredity, are things which are usually true, but not always true.
Yeah, no. Yeah.
I mean, isn't there a danger that the most interesting things occur when they're not true, and that if you set up a process which is based on these principles, that you miss out on these interesting outliers?
You notice I carefully not use the word fundamental, I use governing. And because these slides, in the book or in the writing, an example would be sparsity usually only makes sense when you're screening experiment. You start with many, and in the industrial setting, 20, you know 3, 4 are important. Heredity is for model selection, which you may agree or may not agree, we don't know. The hierarchy, again, it's if you are in a complex situation, like you already move to the surface peak, you don't do hierarchy. So yes, I would say more the early stage screening stage. Yeah, but I cannot. Yeah.
My question is somewhat similar. I work in medical statistics, and when I heard you talking about the heredity principle, I'm wondering, well, there are situations like gene-environment interactions where you're specifically looking at the interaction and there will be no main effect. So the hereditary...
I agree. And yes, and remember I said this for model selection. Actually, gene is a good example, but in some cases, the conditional main effect, conditional main effect is used in genetics. I forgot there's a terminology that is given the expression level of one gene and the effect of the other. So, but that's correct. Yeah. I think Rosemary should be because she raised her hand 4 times.
No, I just wanted to comment. You credited McCulloch Nelda book for marginality, but if you can go way back, that Nelda wrote lots of papers in which she emphasised marginality.
Yes, I apologize. I knew this was John's idea, but yeah, I should go back to this one. I didn't do the search. To save my time, you can tell me what's because I need to write a future lecture. Please send me the earliest example of John, and because I really think John is one of the greatest statisticians. This was Nelda's idea, that we knew that, and marginality was Nelda's idea, but it's happened to be in the book. Yes.
Another comment about randomization. In a physical experimental setting, you use randomization because there are factors which may be affecting the mean response which you're unaware of.
Yeah, lurking variables.
Lurking variables. Whereas in a deterministic computer simulation, you have in hand all the factors that are affecting the response, and there's no need to randomize in that particular case. It's not like there's factors that are changing in the code that you don't know about. So, I mean, I think that's the main rationale for not using randomization in
Thank you. You
deterministic
gave a
computer
much
study.
better explanation, defense than what I did. Yeah, right. Yeah. So you and Johnny, you can talk more about it.
Any other questions or comments? If not, let's thank Jeff again.